time a very serious US university wanted to pick my brain. It was around questions of waste management at Stanford, and they absolutely insisted that I take a 72-hour flight or whatever across to California from Cape Town to spend 2 days there and then fly back. It was an amazing opportunity, but yeah, that's probably around 2015. So yeah, thank you very much for the invitation. We had a few opportunities, well, one or two really just so far, to engage with Gail and the exciting work that you folk do. Yeah, we've got big environmental justice legacies and problems in South Africa, so it's a big opportunity for us to get to tap into the thinking that we do. And today what I want to do is just share our analysis, just one type of analysis with you on this very unique economy in the world, which might provide some interesting ways to calibrate the models you're working on, because it's so unique and so extreme in some of its performances and pathologies. So it's a focus on a material flow analysis, and that shows just how linear this economy is. So most economies have degrees of circularity that are much higher, and so this might in fact be an interesting point as you engage with the physical and thermodynamic aspects tied to the economic. The work was done during 2020 and 2021. The methods that we use here are not mine. They come from a team in Vienna led by Willi Haas, and I'll say a bit more about them later. I contributed 20 years of knowledge in numbers and anecdotes and sources on the physicality of South Africa's economy in relation to questions of sustainable development. They provide the method. I'll try to explain the method today, and hopefully I'll do well enough. But they've written a lot about that method, and the work that I'm presenting on was done for the South African government through a program called the Waste Research Development and Innovation Roadmap, and is kind of starting to influence some policy at the National Department of Science and Innovation. So yeah, just to check then that you so far hearing me very well. Is that all good for everybody?
Yeah.
Yeah, fantastic. Yeah, and our colleagues in Vienna work at a university of natural resources at the Institute for Social Ecology. Yeah, so let's get into it. Make sure I can advance my slides. So this is the order through which I'll go. I'll just start with a few notes on South Africa, the methodology as well as I can explain it, overall results, then a bit of a deep dive into some of the major material groups, and some closing observations on the state of circularity and what that may mean, maybe also for questions of justice and environmental justice. Just a single slide about South Africa. As economists, you're very capable, I think. Are you all economists? Maybe not. One makes assumptions here. But yeah, the World Bank holds a lot of stats. You can click on the link that I've got at the bottom there. We're about twice the size of Texas, both in physical area size and the population. We hold two rather dubious world records, being the most unequal major economy, with a Gini coefficient of 63, I think, on the sort of income inequality measures, and currently an unemployment rate of 33%. We're also the most carbon intensive major economy, producing just 1.2 kilogram of US dollars 2015 equivalent of GDP for every producing a whole 1.2 kilogram for every US dollar of GDP we produce, that way around. And just a little anecdote there. We're the source of Ronald Reagan's biggest foreign policy defeat when the question of sanctions against then apartheid South Africa led to the Senate overturning a presidential veto with not just the required 2/3 majority, but think 79 votes, slapping the president in the face. But yeah, there's probably a lot more to know about South Africa. Our flag on the bottom right, and a map of the solar irradiation on the bottom left. We're a very sunny country overall. Some of the world's best solar resources also found in our Northern Cape province. And the holes in the middle are not where the clouds always cover surface, but the mountain kingdom of Lesotho is wholly enclaved within the Republic of South Africa, but is a totally independent state. And Swaziland, or Eswatini, the last remaining, I think, absolute monarchy in the world, is largely within, or yeah, one of our neighboring states, but yeah, kind of almost looks like it's enclaved by us too. All right, so that's about South Africa. You can look up a lot more about the country. I'm going to go through my presentation largely in a coherent argument. If there are terms I use that are not known to you, please interrupt to get the clarification. We don't always speak the same version of English, but otherwise for discussion, hopefully towards the end. So into the methodology, which is rooted in the field of industrial ecology and the body of work that's called socio-economic metabolism analysis. So it does take the metaphor from the biological metabolism, that an organism, whether it's a single cell or a complex being like a human body, has a metabolism. One needs to understand the intake and the outflows, and what growth there may happen, and what happens inside to transform the inputs to the outputs. And that metabolism can be mass balanced, which is very useful when one applies that first conservation law about mass to make sure the measurements and analyses are consistent. And so economies are said to have a social metabolism, where knowledge of trade, imports and exports can be coupled to knowledge of physical extraction and outflows to the biophysical environment. And those need to mass balance, of course, with an understanding of what is accumulated inside the system. And what's accumulated inside the system are, of course, on the one hand, the people. In our case, the 60 million people to a single digit are 3 million metric tons of weight. The livestock, 7 million metric tons. And the artifacts, and this is a big story of metabolic analysis in the 20th and 21st century, those are much, much more biomass than the living beings, at least the humans and their livestock. Of course, the biophysical environment would also weigh in very heavily. That's not quantified here. The estimates courtesy of my colleague Willie Haas. And yeah, as we've already said, that can be mass balanced. In the field of socio-economic metabolism, I like to distinguish the analysis of material flows, which is well documented and has even a standardized methodology in the European context through Eurostat, from energy flow analysis. Sometimes these are combined in MEFA, material and energy flow analyses, and then somewhat separate water flows are analyzed often by different folk. Sometimes in the nexus approach, you may be familiar with that. I'm not going to cover the water flows here. I'm going to mainly focus on material flows. I'm throwing in 1 or 2 slides on energy flows, since we also have an energy balance for the country in our energy systems model that's coupled with the CGE. And that's part of the interest in a potential collaboration. So for the material flows, the method, one needs to understand the scheme that's used, what is counted, and where are the simplifications. So let me also get a pointer. At this point, that will probably start to be useful. So one needs to have information on the biophysical trade balance. Trade figures are probably good data sources that you're very familiar with. They're widely available. And then one needs to have a knowledge of the extraction from the economy. That's agriculture, fishing, mining, farming, forestry and maybe hunting. On the output side, one needs to have good waste statistics and emission statistics. The particular scheme we use here has been described by Haas and partners repeatedly. It is an advance on the standardized economy-wide material flow analysis in that it really does also quantify the recycling loop, the so-called socio-economic cycling loop, by defining these categories of processed material, which is all the material imported, extracted, plus recycled, that then enters for energetic or material use. Energetic use includes technical energy and biological energy, so food and feed. It's part of the energy use. It accounts for in-stock or materials that are in use in the form of various stocks. It then accounts before things go to recycling for an interim output category that combines end-of-life waste with emissions and vapor. Right, so that's the important part of what's in the calculation engine behind the numbers that I'll show you today. Question of what is cycled ecologically is a big topic in circular economy these days. We understand that the butterfly of the Ellen MacArthur Foundation has two wings, and earlier scholars also used the biological and the socio-technical system to describe cradle-to-cradle systems, etc. So ecological cycling is an important element that is accounted for here as well. And this, just on the ecological cycling, there is the theoretical of what could be cycled, and then there are disruptions of the natural cycles in the kind of criteria that are listed here. The renewability really is limited by any of these. In terms of the accounting, the metrics, and I'll show you some later for South Africa, the method develops these both on the input side of the economy and on the output side of the economy. And it stacks up the processed material into the part that is socioeconomically cycled, the part that's ecologically cycled, and the part that's non-circulated. On the input side, that means it's extracted from nature. And then on the output side, it does the same, but the input side and output side differ by the net addition to in-use stocks. Right. This method has been used extensively, and for me, this is one of the most amazing pieces of work by our Austrian colleagues, where they applied this to all material flows on the planet from 1900 in the top graph right through to 2015 in time slices. And they just show how the materiality of the world economy, the global economy, has gotten bigger and bigger, but also somewhat more circular over time. Or at least the flows circulating are no longer trivial. And there's the title of that piece of work. And I really just want to say that the method has been extensively used, and that this, if you haven't seen this, a fascinating paper on really one of the ways that this big global acceleration of humankind manifests and puts so much pressure on the planet. Just some terminology that, if you haven't come across this, is useful to know. Domestic extraction, I think, it's already defined itself almost. It's important to distinguish on the waste side between extractive waste and unused extraction, where extractive waste is material that has been extracted and processed and is then rejected from a techno-economic system, with unused extraction is really material that's only been moved but not processed. So there are some examples there. If the stover is left on the field, we could argue that the machine, the big combine harvester, has processed it to some extent, but but if it's left on the field, we don't count it. in mining, the overburden and waste rock, we don't count. These can be massive flows relative to what is actually processed and then becomes waste. Difference between fresh weight and dry weight, one needs to be aware of those. And then when we talk about metal flows, in this case, we really account for the element only. And so our metal flows are somewhat smaller than trade statistics would show for traded ores, for example, where sulfur, oxygen are still part of the ore, but we count only the metal when we talk about metals. Yeah, right. And stock building materials are products that stay in use for more than a year. To the South African study, this gives you a bit of a sense of the scope. We picked 2017 as our year of analysis because there was a national state of waste report available for that year. One cannot do this without semi-decent waste statistics, and we don't have these on an annual basis as yet. There are 5 major categories that one pays attention to, and then they get subcategories, and I'll show you some of the examples of what's in the subcategories. And then to a third digit, the number of materials. Bit of a novelty in this piece of work, we introduced synthetic materials that you cannot extract from nature, like steel, glass, concrete, asphalt, and plastics, to facilitate some of the circularity accounting. So a bit of methodological novelty in this particular work there. That gives you a sense, 82 material categories overall that form the major rows in the spreadsheet. So then let me get into the result, the main result, which is in the form of a Sankey diagram. May I assume that everybody knows how Sankey diagrams work? Essentially, the thickness of a line is just proportional to its size. So the thicker a line, the more prominent this is. It's very intuitive. So this is the overall picture, and I'll talk you just a little bit through what makes up the various components. You can already see a very linear picture in the fat flows and a little bit of circularity at the bottom. I'll quantify that within 2-3 minutes from here. In material terms, we talk in million metric tons, and the domestic extraction far outweighs the imports. In terms of materials extracted domestically, biomass is non-trivial at 17%. Metals make up 7%. The color codes up here to the right. The extractive waste from mining adds another 23%. And then your non-metallic minerals at 17%, 30% fossil fuels, domestic extraction, and 6% additional, the extractive waste just from coal. On the import side, we also see of the rather small total imports, crude oil dominates. We don't have any domestic crude oil of note. The exports are dominated by metals and coal, essentially. So you see the orange there representing fossil fuels, that's coal. The processed material is a good spectrum of materials, of the material groups. We include at this stage the extractive wastes as they are actually processed. The ores and the run-of-mine ores are milled, and the ore of interest is separated from a very fine powder that then has to be disposed of, called tailings in the mining industry. Energetic use, say, is technical energy and food and feed. So the biomass, there's not all biomass going to technical boilers, but it's for what the domestic livestock eats and what people eat. And on the material side, we start to see the non-metallic minerals really playing a significant role. Next bit is on the interim outputs. It should all balance up. Reuse and recycling pretty small, 14 million tons in total, and the makeup is shown here in these two bubbles. Actually, a fair bit of non-metallic minerals in the reuse in our estimate, and the socio-technically cycled material, also including some biomass-derived material. That's primarily paper and cardboard. And just going through to the end. The emissions, 180 million tons, that's mainly carbon, and we account here for carbon, not for carbon dioxide. We've double-checked that to the national emission statistics in terms of carbon dioxide, and the number is consistent enough. Great. I think that's the picture. And then ecological cycling, bit of an estimate we had to make there, a fair bit of uncertainty how broken the ecological cycles are. This is our best estimate, 37 million tons, fair bit more cycled by nature than cycled by the socio-economic means. Right, yeah. So the indicators that the methodology promises on the input side come to just under 2% for the socio-economic cycling rate, 5% for the ecological cycling rate, a total circularity assessment on the input side of 7%. On the output side, that's slightly higher because the output in total is a bit smaller than the input. Right, that's the highlight of the results. Sometimes I stop the seminar here or jump to the conclusions, but I believe I have a bit more time and understand a little bit what's really inside these calculations might be of some relevance here. So before we can get there, we need to spend a little bit of time on the waste statistics, how much waste is actually there, and how the official waste statistics map onto what one does in a material flow analysis. Municipal solid waste, we largely agreed with the official statistics, but we added 4 million tons for the households that do not have official waste collection, and who dispose of their waste in unregulated wastes. Most of them are in the rural areas. And that causes very significant problems, especially around the plastics debate. Construction and demolition waste is significantly underreported. This is apparently a global phenomenon. We're not unique there. Sewage sludge wasn't in the waste statistics. We added it. Biomass, we scaled down by 8 million tons because a fair bit of the biomass actually burned, especially in the sugar industry and in the forestry industry for technical energy generation in the mills. And so it's really just the ash that becomes a waste, not the bagasse or the wood pulp, or the bark. Right, but yeah, overall, our deviation from the official statistics fairly small. 111 million tons is our estimate. I think I've mentioned that. Then we have to add what's not in the official definition of waste, 170 million metric tons of extractive waste from metal mining, and 50 million metric tons of extractive waste from coal mining, for a total of 330 million metric tons of solid waste, essentially. Right. We spent a bit of time, it's also a methodological novelty, to try to estimate what may happen to construction and demolition waste. And given that we've got such an unequal society, we have a large informal reuse sector where people collect from demolition sites, and companies to some extent move the material through to a market of people who build their own homes, literally from whatever they can lay their hands on. Sometimes that's an active market. You can go to such a demolition market and buy an old window frame or door frame or door, or collect bricks or whatever. So yeah, we had two methods to estimate that, and I don't think all that important here, but we've written that up in a separate paper if anybody is into this kind of stuff. Let me go through to the major material flows now. South Africa, of course, is known to many outside historically as a major gold producer. In terms of the metals, the amount of gold is very, very small. It's 120 tons, metric tons, not million metric tons, but just 120 tons. But the extractive waste from that industry is still very sizable at probably around 40 million metric tons out of the extractive waste of 172. But the gold industry has almost become a museum artifact in South Africa. It still contributes very nicely to the national and to the export income because of the very high gold price. But we've dropped to number 7 in the list of countries that are gold producers, because the gold is essentially been depleted. There's only one very large, very rich gold mine that still produces at scale, and then the rest of the production comes from the reworking of old tailings. But there's a whole lot of other metals in the picture. This part of the Sankey diagram really just emphasizes that on the light blue, the metals, we export much more than we use. But on the dark blue, the extractive waste, of course, that remains in the country. And that is always a question of justice to some extent. And maybe that's in the international sense as well. Yeah, just to give you a look under the hood for the metals, this is how it looks in the spreadsheet in terms of categories. There's the ferrous metals, the iron as one category, and then the non-ferrous metals making up the others. And yeah, down to quite an exotic list at times. The real big ones, iron ore is traded at large amounts, and remember, this is only the metal component. And then the non-ferrous metals, let me just see, the sizable ones really are chromium and manganese, where South Africa holds the biggest reserves globally. It's not necessarily the biggest producer. And then, yeah, so I think that gives you a first handle of where the big flows are. The mining sector is quite complicated to do accounting in because it's not a question that you have one sector that does one product. The different metals often occur in the same ore, and then some mines pull out multiple different ores that are co-associated. Iron is not only produced by the iron ore miners and the steel sector, but there are iron byproducts from the manganese and chromium industries. And the chromium industry in turn gets concentrate from the platinum mining industry, which then passes on some iron through ultimately into the steelmaking industry. Yeah, and so this platinum mining industry does a lot more than just the platinum group metals, even including some of the novel energy metals like cobalt, where South Africa is the 3rd largest producer globally, I believe. Right, yeah, so just giving a sense of the complexity of the counting that had to be done. Here's the Sankey diagram just for the ferrous metals, the 3 big ones, iron, chromium, manganese, and how those relate to steel. And you can see that exports really dominate this picture. And where we do make steel, there's a pretty decent circularity in the domestic steel sector. And of course, there's a whole lot of associated extractive waste. The balance between metal and extractive waste isn't all that bad in these large volume metals, very different to the precious metals, of course. So this is one of our first characterization. If you look in here at an economy that is materially dominated by export-oriented extractives, and Willie and I are just finishing a paper for resource conservation and recycling in which we unpack that and compare it to some extent to other extractive economies. Yeah, on the non-metallic minerals, it's really largely about what we add to the domestic stock in the form of concrete, which in turn is mainly sand and gravel held together by cement. And to make cement, you need to mine a few other things like limestone and fluorspar. There's a fair bit of also dissipative use more on the industrial minerals side than on the construction materials. The material classes here essentially split between the industrial minerals, and the construction minerals. In the construction minerals, you do see the gravel and sand as a major category. Sand sustainability is a global topic, starting to become on here too. But yeah, chalk, dolomite, limestone, those that go into cement making, of course, also important. Chemical and fertilizer minerals dominating on the industrial minerals. Over to biomass. Here I'll start with the Sankey, so with a good old-fashioned pie chart in terms of what is extracted from nature. Dominant is what domestic animals graze, and then fodder crops added to that. And then primary crops, so this is large area-based cereal agriculture, but also sugar crops are the dominant ones in the primary crops. But it's a very rich agricultural system, and on average, this is one of the few countries that produces more food than its population needs in terms of calories and diversity. There are a few categories where we're not self-sufficient, including, for example, the oil-bearing crops. Actually, not a little bit. A sizable amount of timber is extracted as well from an industrial kind of forestry. And wood fuel remains a significant source of energy for poor rural households, with fairly dire consequences for both ecology and human health. This is what the biomass categorization looks like in the system. Again, just really to get an impression for what's under the hood in these methods. The pie chart's built on what's on this particular side. See, there's something in the chat. Right, okay, not important for me. Good. So let me get to and then the biomass Sankey really is dominated by what goes into energetic use, being food and feed. There's a big sustainability discussion around so-called food waste. So it's important to understand the definitions there. And how all that material ends up. Also the end of life disposal methods. There's a policy imperative to remove organics from disposal to landfill, and so composting and other alternative treatment methods have been gaining ground. It's important to try to get statistics on that in these methods. Some material use, both in terms of additions to stock in the form of timber. We don't build that much with timber. We're really a bricks and mortar type society, but there is some timber construction and timber used within bricks and mortar houses, for example, in roof trusses. And then in the throughput, there's of course a sizable amount of paper and cardboard. And a good recyclability, but I'll show you that later. So the bio-based flows, also to characterize this economy, it is biologically diverse. It's got 7 different biomes, at 17% of domestic extraction, this is pretty sizable. We really found very significant sustainability concerns, both on the input side in terms of sustainable harvesting, use of chemical fertilizers and pesticides, and on the output side in terms of unsustainable disposal methods. Just a little bit of South African reality. It's a light relief slide. This is one of, or maybe not, in relation to that fairly extreme poverty head count of 20 per 100. One of the most important staple foods in the country is maize meal, what you call corn in the US. In a good year, we produce 15 million metric tons of it, which is definitely enough to feed the nation, not just directly, but it's about only a third that goes to human consumption. But it can be for a poor person 3 times a day that maize meal is on the menu. I've thrown in an energetic analysis here for those who think about energy terms. I'll show you an energy Sankey diagram just now, just to complement the material one. but it stacks up against gasoline and diesel in a non-trivial way in terms of what we grow to feed our nation. Fossil fuels, I'll start here with what's under the hood and then show the Sankey diagram next. But it's really dominated by domestic extraction of coal and a little bit of natural gas that's domestically extracted. I'm not showing the imports on this particular slide, but yeah, that's how it's linked. It's categorized here. In the synthetic categories, we've introduced plastics here because we also make plastics from coal through an interesting process that essentially we make liquid fuels from coal and then some chemicals which can also become plastic. So there was a unique bit of accounting to be done in the methodology. Yeah, fossil-based material flows, that's a Sankey diagram. Of course, fossil fuels mainly are there for energetic use. There is very sizable solid and liquid outputs, especially the ash. Single largest category of solid waste in the official statistics are coal ash. And then in terms of what is recycled, plastics is doing reasonably well, but that doesn't make up for the 4 million metric tons. Most of what's actually in the recycling loop is coal ash that goes into the construction sector. So there's a bit of circularity in some ways associated with coal and coal for energy and the coal ash. Right, yeah, so that's the fossil-based material flows. Right, and then to just complement that, a quick step over to the other line of work that I'm involved with through our energy systems research group. Here's a Sankey diagram in energy, in energetic terms for the country, that also shows this very strong dominance of coal, sizable amount exported, but the coal is then used to a larger extent domestically for electricity generation, to a smaller extent to make liquid fuels and chemicals through the synthetic fuels process that's unique in the world, and to a still sizable amount for industrial heating. So when industries need heat, they very often use coal-fired boilers rather than gas. We do import a little bit of natural gas from our neighbor Mozambique in the main, and we import our crude oil from Angola, Nigeria, and Saudi Arabia generally. And we then complement that with about a quarter of our liquid fuels are made from coal. And then we also import some already refined liquid fuels. Increasingly, this work was done in 2017. In fact, since then, 2 of the 4 crude oil-based refineries have shut down. All right. Yeah. So that was the look under the hood. I'm going to allow myself another sort of 5 minutes of some analysis and conclusion, if that is okay. Yeah. Good. So firstly, on pockets of circularity. So, it is a very, very linear economy, which may be useful if you want to calibrate a model before you add circularity. But there's pretty good circularity around the metals. These are very valuable, and when you have a lot of poverty, then high value stuff lying around the landscape gets recycled, often even before it's due for recycling, and that infrastructure theft of copper, for example, is very, very significant in terms of how our infrastructure currently is performing for rail and also electricity systems. So yeah, very good circularity. Sometimes circularity is too good. It shouldn't be that high. But yeah, that's the one pocket of high circularity, and that's really just driven by value. Then in terms of construction materials, quite challenging around concrete, but there is a big factory down the road I like to take my students to see what does it look like when you crunch up 100,000 tons of demolition concrete a year to extract the sand and gravel and use it again, and of course the metal to sell it off. For wood, the recycling of paper and the reuse of timber from construction demolition sites are non-trivial. And clay bricks, this is a stab in the dark, but from observations and just a bit of logics, we think there's actually pretty high informal reuse when those can be recovered from building sites without them breaking. Maybe a tad too high, but some further work needed. Plastics is challenging. We're certainly doing much better than the US in terms of our plastics recycling rates. At least when I last was in Stanford, there was a big, oh, really? How do you do that? Essentially, we do it like California does it, but the rest of the states don't believe in something called extended producer responsibility, I believe. It's a swear word. Maybe that has changed, but we're introducing that on top of a system that has developed out of a pure hunt for value, coupled to some environmentally conscious producers. But overall, still a lot of work needed around circularity in plastics. I've also published separately on the plastic circularity. Container glass is probably the biggest success story. So this mainly driven around beer bottles. So our beer drinkers in the country really can feel that they generally participate in a very circular enterprise, and that both loops are very active: the collection and reuse of bottles, and industrial cleaning and refilling, and then the recycling of glass as well, container glass. So that's on pockets of circularity, both through recycling and then reuse and cascading in this highly unequal economy. Just in terms of could the circularity be much higher than it is, it's a worthwhile analysis. So a quick reminder of the 7% total recycling on the input side, how that is made up, and that there is indeed some uncertainty to it. The next slide then goes to could it be higher or not. But yeah, just a little bit of uncertainty analysis done around this as well. One has to say that these are often quite uncertain estimates. You're relying on statistics where not everybody reports, and so on and so on. So we've put that around it. But yeah, to the analysis, how much could really be recycled, and this is better done on the output side, where we have a total of 630 megatons of outputs, and only 52 of those are cycled, of which ecological is 37 and socio-economic is 14. What is the potential really? So theoretically, you have the processed materials of 746. Take away the emissions, carbon emissions, very hard to imagine being recycled, although we do have the topic of CCUS appearing on the horizon. The water vapor, which maybe ecologically you could say is cycled, and then dissipative use, which you really have to design out of the system. Then we have the extractive waste from coal mining, extractive waste from metal ores mining, and the net addition to stocks. Those are not really up for discussion. There is some reuse of extractive waste of coal mining, but not that much. Extractive waste metal mining is really such a large thing. One can make some construction materials, but yeah, it doesn't match up all that well in terms of quality you need. So essentially, there's 103 million tons for reuse and recycling, and out of those, 14 are recycled. So the socioeconomic cycling rate would look like 14% rather than 2% if one does it that way. Still a lot of work to be done. Right, yeah. So then one other observation before I conclude, and that is that we found a rather low rate of domestic stock building. Only 15% of what is extracted is added to stocks in our economy. In the EU 28, that is 60%. In absolute terms, that's 2.3 tons per capita in our society relative to 8 tons per capita in the European Union. So very low stock add. And yes, if you have 40% of your population that doesn't live in a decent house, 20% that doesn't live in a thing that could be called a house, really, you're adding too little to your material stocks. If only 20% of people own a car, we could argue whether that's a good thing or not. But in other societies, there are a lot more cars around, and therefore the domestic stock add is a lot higher. So here are some numbers from China from 1995 and 2015 to just say it's not just that we perform less than the EU, but also poorer than China in 1995 and much poorer than China in 2015. Incredibly high numbers there. And the per capita stock ad is shown here on another graph. Ours on the extreme right at 2.3 tons per capita. And yeah, we're significantly lower than most others. Sure, we got the US on here, industrial old world. I guess that's you. Sure, is that, are you a new world? Maybe you're a new world. Anyway, yeah. So this is an interesting finding that is borne out by economic commentary, of course, that the infrastructure investment has been consistently too low. To summarize the findings, my last two slides. The findings have all appeared earlier. So the dominance of export-oriented extractives to a large extent is a habitus inherited, in our view, from the colonial conquest. The colonies were there to provide raw materials back to the empire. The energetic dominance of fossil fuels is not surprising, but it's extreme in our case. Is coming down. And electricity production, for example, has dropped from 92% coal-based to 82% coal-based over the last decade. So there are things happening. The sizable footprint of bio-based activities should not be forgotten, and that there are very significant ecological cycling concerns or sustainability concerns. The low rate of domestic stock building probably has a fair bit to do with the socio-economic malaise of very high inequality. And then the pockets of high circularity are noteworthy for those who want to improve circularity. What's already done, what's still possible, what's not possible when you have an export-oriented extractives focus in your or business model for your national economy. Last slide, how to move forward, how to get from a model that is probably not sustainable both ecologically and in terms of where world trade is going to be moving in the shorter term for carbon and in the somewhat longer term for metals, because the users of metals will cycle those. There are very welcome resource rents associated with this. Some of those aren't finding their way into our fiscus, making sure they don't leak into other foreign domination is always very difficult. Power generation I've mentioned, and that the waste related to extractives and coal are more than 50% of all outputs to nature. One probably wants to move to a system that looks more like the one on the bottom, where we have somewhat less focus on the extractives and the exports. Earning export income, of course, always important in macroeconomics, but yeah, less going to nature and more being cycled, and the cycles and the processing driven by solar power rather than by the dark power inherent in what is called the minerals energy complex here. And that would require very substantial changes in mining and agriculture, the extractives, but also in how the domestic economy is built around transport systems, urban planning, the power sector, and various service sectors. And that will require a lot of research, innovation to change and driven by a systems focus. That's it. There are some acknowledgements to the people who contributed and to those who drew the diagrams that get us so much attention. So that's in particular Doris on the material flow and Josie on the energy flow, Sankey. And I'll stop it at this stage. Thank you very much.
Thank you very much. So I guess we could go for questions now. If well, we'll try to just speak this way, and we'll see if you can hear us from the whole room. But maybe you might have to come to my computer to talk. I'm not sure.
Right. Let's see.
have a question for you, Harro. Thank you for the amazing presentation. Can you hear me?
Yes.
Okay, good. So maybe I missed something, but I did not see where you took account of water in the whole story, because you mentioned it at the beginning, and then I didn't see it. Maybe it's included somewhere in the biomass analysis, or tell me if I'm completely wrong.
Yeah. So essentially, what we've done here does not include a water account for the country. It is usually excluded in the economy-wide material flow analyses. The only part where water is accounted for if it is inherent in the extracted materials. So that is, for example, in the biomass, where one has to balance it out in the mass balance. And where water vapor is formed by some industrial activities, for example, when you burn the clay brick and so on. So there's some water vapor formed through combustion. So but the water account is not included here. There are other people who've done those, and I've done one at some stage when Cape Town had a drought problem and the so-called day zero threat. We did some water accounting for Cape Town, but yeah, this is something we would have to draw in separately for envisaged work going forward. We've done a bit of water energy nexus work, so national water accounts are available, and it's a big sustainability concern as well. But yeah, not included in today's slides.
Okay, thank you. And my second question is about the question of the issue of housing. So you mentioned that so many people in South Africa don't have a decent house, and that this might explain the very low material footprint in terms of stocks per capita. And so in the ideal picture that you show us here on your slide at the bottom, how do you deal with this question? So let us assume that everybody has a decent house. I guess then the material footprint would increase significantly. How would this be compensated?
Yeah, no, absolutely. That is actually one of the findings, that we are probably not producing enough of the core old industrial materials, being cement, concrete, extracting sand and gravel from nature, and making steel. So with a focus on extractives, the brightest minds and engineers end up in the pay of companies that extract gold and platinum and coal and sell it overseas, rather than being architects and civil engineers who build amazing buildings for people to live in and be sheltered. So one level of analysis is, if we follow the older model of the built environment being just bricks and mortar and steel, then the extraction may have to increase. I mean, an attention to what one can recover and recycle definitely would help. The other interpretation is, one really needs to see innovation and lighter weight materials and more sustainable materials flowing into the construction sector. And there we have a very active Green Building Council and Green Building architectural scene. We've seen the first high-rise building in the city centre here in Cape Town go up with something called hempcrete, where hemp fibers have been mixed into the concrete, making a 40% lighter concrete, but a stronger concrete. And that's claimed to be a world first for a high-rise building in a CBD. I'm not quite sure that I can support that. I haven't looked whether that claim holds, but yeah, so there is innovation there. And circular economy, so one's trying to do both here, to catch up on the socio-economics, but to do so by following best developments around low carbon and circular.
Okay, thank you.
I think Grégoire has a question.
Yes. Can you hear me well?
Yes.
Yeah.
Cool. Okay, so thank you, Harro, for your presentation. It was very informative. I have a few questions. Some might be very basic because I don't know the whole literature yet, but maybe you can orientate me. If I may, I will just say all my question, and then you pick and choose those that
Sure.
you reply. Okay, thanks.
Good. Go ahead.
So at the beginning, you coined the metabolic view of the economy as metaphorical. And I wonder why you took that precaution, if you think that somewhere there's a fundamental difference with other type of organisms. Then I was wondering whether it has been assessed somewhere in the literature, if there might be highest maximal attainable rate of circularity that an economy could reach, because all materials are not as easily recyclable, and maybe some are essential to a certain type of economy. Yeah, you see, there might be some technology limitation, but some might be impossible to overcome. There might be limited by the mere laws of physics. Another thing that I wondered, with the Sankey diagram, you were plotting your data for a given year, sometimes different years, but I wonder actually what data are available for South Africa, whether you have full time series of this material flow for the past 20 years, or if you can just inform me of what is available to try to work with those data. And related to that, I was wondering whether maybe you were able to identify or quantify maybe some link between the material and energy intensity of an economy and its prosperity. Because this is, or it has worked until now, and although we should be aiming at different trajectories and redefining a few concepts, I mean, I don't know much about that question. And I wonder, of course, if you explored that type of question for the particular stance of South Africa. And the last thing I wanted to say is just some advertising, maybe. Exactly at the same time as we were having this meeting, there was the autumnal reunion of the Exergy Economics Network. And I rapidly checked, and I haven't seen you in the mailing list, but I do have seen two people from Willis University, Nina Eisenmenger and Andreas Mager. So I don't know, maybe you would be interested in joining the mailing list, because there's a few people doing things in your domain applied to different countries, but of course the methodology overlap. So that's it.
Right. Fantastic. Wow, that's some really good questions. You listened very closely and are thinking very deeply about this. I'll try to answer them, written them down. The metabolic view, is it just a metaphor or is it for real? Yeah, of course. The aggregation of the metabolism of individual individuals in a society makes for a societal metabolism. A beehive or an ant colony has a metabolism that's physically demarcated around their boundaries, and so yeah, cities really do have a metabolism, and countries really do have a metabolism. In industrial ecology, we do kind of recognize that there's a part where it's physical and a part where it becomes an analogy. So maybe in the accounting sense, it's real. The other side of metabolic studies is about how the metabolism is regulated. And when you start to say what are the hormones and enzymes in the biophysical economy, you're already starting to use an analogy. And I gave a talk on this topic to lawyers 2 days ago in a colloquium, and I said, that's exactly where you come in. You are the people who work on the organs that express the enzymes or the hormones, right? You know, the regulation in society. They found that quite quaint. But yeah, hopefully that's given you sort of a take on is it metaphorical or real. The highest rate of circularity attainable, I've not seen, but I've also not specifically looked for that. Of course, it would be expected to happen in a more mature society where the stock build, you know, the addition to stocks, or the net addition to stocks becomes quite small. In younger societies, younger ecosystems, you'd have a bigger stock add. Yeah, and it's not really so much about the circularity in the end, but about bringing the extraction from nature to within tolerable limits, or and the excretion to nature, if I can put it that way, to within regenerative limits. You know, sorry, regenerative limits on the input side and absorptive limits on the output side. So that's so you don't need to aim for full circularity. You need to be within the carrying capacity of the ecosystems. But having said that, there's been some work done on circularity around some materials, and metals in particular have been studied, where one would expect very high circularity because of the high value. And the International Resources Panel a decade ago brought out some publications on the circularity of metals. There's this very evocative periodic table of the elements coded by color to show whether the recycling rate is less than 10%, between 10 and 50%, or higher than 50%. And one of the lead thinkers around the thermodynamics of circularity in the system is Marcus Reuter. He makes the point that at every transformation in the system, whether it's a technical transformation or an economic, trade, and you know, the logistics of recovering materials, every step you have losses in the system, and those losses in a loop multiply up the inefficiencies, as you would, you know, 2% dissipation here, 2% non-collection there, 2% inefficiency in a physical separation in a recycling plant. They all add up, and you cannot hope for 100% circularity, even around a highly valuable metal. It's just unless you put infinite amounts of energy into it, right? So yeah, so there's a kind of link between circularity and energy input there, which probably would be a link over to the exergy economics kind of type of analysis, which I'll pick up later. You then asked about data sources.
First, can I ask you please to write down the name of the thermodynamicist that you cited? Because I didn't catch.
Yeah, sure. That's get the chat. Marcus Reuter happens to be a South African, but who's worked quite extensively globally on this topic. So, like the news agency Reuters. Right. Yeah. So on data, there's a lovely slide in the paper that Billy's team put out when they presented this kind of analysis for the European Union, just in terms of where the data sources come from. The one for which time series are nicely available is the trade statistics. So there's lots of databases. Comtrade tends to be used quite widely, and so you have your data series there. For others on the extraction side, agriculture, for example, FAO statistics, or USGS. Interestingly, the US often has much better stats for other countries than any other agency. So United States Geological Survey has pretty decent time series for South African metals production. Not always accurate enough, but a good source to work with. The real reason why we can't do this currently on a year-on-year basis on the waste statistics, because we need to mass balance the waste on the output side back against the input side, and then infer the addition to stocks there, because addition to stocks, nobody keeps records of those in a comprehensive way. We chose 2017. Some of the data that we may have pulled was slightly here or there on other sides, but by and large, what I've shown you is for 2017 snapshot. We're talking in our energy systems group, we're on our CG platform, whether we could at least get some of the materials, the bulk materials like iron, steel, concrete, projected and tied directly to macroeconomic projections, and then start to populate a forward-looking material flow model linked to how the economy might perform. So that's the data question. Is there a link between material and energy intensity and prosperity? Firstly, is there a link between material and energy intensity? There surely is. We've only partially analyzed that. So that's something that we should probably aim to build a few more metrics from our energy systems model. Whether there's a link between the intensity and prosperity, I really don't know. Kuznets curve comes to mind, and I'm not an economist. I would tend to think that initially, the more intensive you get, the more prosperity you generate. But at some stage you go into a dematerialization stage where you offload the manufacturing and extractives to others, and you focus on an economy that's dematerialized and service heavy. But I haven't engaged with that topic a lot. And so, of course, when you use a consumption-based accounting, for example, greenhouse gas emissions, what do you mean by greenhouse gas intensity within your own national borders, or causally tied to your consumptive habits? Okay. And then lastly, thanks for the note on the socio-economics network. I've come across them here and there. There's so many networks that I'd love to be part of if I could split myself into several. One of the things you'll learn when you work with South African academics of any walk of life is that we tend to be much thinner equipped with bright minds than other societies. Part of our socioeconomic malaise and inherited inequalities. But our student to staff ratio in the university is about 4 times higher than yours. And correspondingly, our researchers are thinly spread and tend to be jacks of many trades. And so I'd love to, but if I start talking exergy, I completely lose the little bit of government attention that I currently get. Who understands CO2? So we'd love to do more, and there's great insights to be gained, and so I read when I can, but we find that we often we might have a student that we can send off to participate in those networks, but often we just can't be in all the exciting spaces where knowledge is being pushed at the boundary. And so collaborations with institutes in the global north that have this much more depth can really also help if we design them well and we feed the core insights back into ultimately a policy speak that's understandable by the decision makers here. Hope that has answered your questions.
Thank you. I think Paul, you had questions as well.
Yeah.
Maybe.
So can you hear me if I speak like this?
Yeah, I think that works.
Okay, I can go closer. I was wondering about the different units that we use to calculate all these material aggregates and the consequence in terms of the way we see the system. So for a purely physical approach, I totally understand this aggregation on pure mass. But something which tickles me is that we know very well that, for example, coal, palladium, or gold doesn't have the same mass footprint for the same use. We don't need that much of gold for a large effect, but we need a very big mass of coal for a large effect. Same thing for uranium and coal. So is the fact that we take into account all the waste from the extraction counterbalancing for that phenomena? Could we try to shift a bit the picture and avoid that effect? Count in terms of embedded energy or in terms of labor time spent into each part? And do you know if one, some people have tried to do that? Second, if the data is available or could make it possible? And third, how will it change the picture?
Yeah, accounting for mass just because we can doesn't mean that it's giving us any useful insights. I would say this is a base exercise of which more sophisticated analyses can and must be made. And I've worked, this is my first very serious bit of material flow analysis in a 22 or 24-year career. I've done a few smaller ones before. I've worked extensively with environmental life cycle assessment, which always needs to come off the mass balance of the system in the first place. So one could throw a life cycle assessment on top of this and then start to get a quantification of and a baseline for say 15 major environmental midpoints in life cycle terms. And that's probably a piece of work that should be added on top here. Likewise, to bring in indicators of socioeconomic value creation or externalities in socioeconomic terms, in monetary terms, or other indicators like whatever labor intensity would be very, very worthwhile. We've not done that here at all. I know that Willy and his team are kind of starting to think in this direction for their work and are putting some economic analysis onto their Austrian material flow to get there. And I don't think Willy has joined the call today. If he has, he can speak for himself. Yeah, he has. So yeah, there's big credit to Willy and his team. So the methodology, I've hopefully explained it well enough, but you can read up on their publications. So Willy, maybe you want to add something on where you are with adding more sophisticated socioeconomic analyses to the pure mass flow system.
Yeah, sorry again for being late, but you know, we have changed our time and I forgot about it. And I was just thinking I'm on the same time like South Africa. Yeah. I mean, there are several different things I would like to say on this topic. The one issue is that we realized that having a good understanding of the material flows is a first step to hook on all different kind of questions. So for many things, you need to have the material flows in tons for different materials in order to make further analysis. So that was one understanding, and many questions you had, I think, along the line that then you need to have some multipliers there or to have something to hook on it. There were very interesting studies by people from Sweden, from Lund University, who have done this embedded labor on a historic base to look how much labor time was embedded in certain kind of products imported, and I think they're very insightful. what we are doing now is more that we look into our biophysical model and introduce a decarbonization strategy, and then look into how does this change the certain investment and consumption, and then the economic modeling is doing some understanding what is if we spend less money on certain things, what might be the kind of shifts that are already included in the economic models, and then we think about shifts where we think there are problematic shifts that might occur. Then we think about shifts that are favorable, and then to look what kind of measures need to be implemented in order to avoid the bad shifts and to have benefits with shift in a direction that are less material intensive and less energy intensive. So these are the things we are doing now, and when we have done this in the economic model, we go back to our biophysical model and implement it again. What does it mean? And to understand, essentially to understand the rebounds that are embedded there. And the rebounds might be in different levels and corners, and we want to find out.
Great. Yeah, hopefully that's answered a very important question. Yeah, certainly not just for its own sake, but as a base to analyze or build other analyses on. Back, Clémence, are there further questions in the room?
There's no one.
Yeah,
Okay. Oh, okay.
I would. So the first thing we are trying to on that specific question of embedded labor time, of this type of things, we're also trying to push our models toward the dialogue between economic and socio-physical system. And so I hope, like, in the following month, we will have things to present to you that can link both theoretically in terms of data, but like we will see in the following month. And the second thing was, especially on that slide, which I found, I think like the key is here. However, I think it could be interesting to try to put more intermediary steps between the initial and the final circularity of the system we have, because from what I understand, if we want to get to the final system, we need more circularity, and we need to change the infrastructure and the type of system which can produce it. And so how can we transform this arrow into specific steps which allow us to go to that circular system? How can we find ways to have, again, for a big enough time, a bigger part of the production which is going into the stock creation to change the metabolic structure of the society and its metabolic properties?
Yeah, I think that's a perfectly fair question. The ability to predict what these diagrams may look like in response to policies and measures introduced is I think one of the cutting edges in the modeling world. We hear that folk who've done this for energy systems, such as at IASA, also in Austria, are adding a material capability to the message platform. We're certainly thinking about how to predict that forward. Yeah, I'm tempted to ask, because anybody knows whether we can automate the creation of these wonderful diagrams. Where's our energy Sankey? We do these on an annual basis. Well, we don't do the diagrams. We have got the data on an annual basis, and we have 64 scenarios to net zero from here to 2050. Whereas at this one here, but it would make fantastic animations if one could just add a Sankey builder on top of Tableau. So if anybody, yeah, so it's a little aside here. But then you can start to ask if you pull particular levers, how does the shape of the system evolve as you going for more circular and lower carbon systems?
So
May I add something here? I mean, when we deal with this issue, there is, first of all, there is this big problem of the societal stocks for our from roads to buildings and so on, and they always grow. This is one of the big problems we have, that since they grow, we have a development in the system that really goes in a different direction than what was shown before. Yeah, exactly in the opposite direction. And what we did when we thought about it, how to change this picture, is always to look at certain stocks and what kind of stock replacements we need. So the first thing is no extension anymore, and then what stocks are more less material intensive, and there we look into maintenance and operation in specific terms. So which stocks need very little kind of maintenance, are long lasting, and do not need too much energy for operation. So there you can start then for example, for buildings, to look how you need to change buildings, or the electricity sector, or the mobility sector. And these are important issues to change these kind of flow characteristics of this one way or stockpiling kind of economies.
Just on a technical thing, I know that in Python, in the library Plotly, there is a module to automatically implement Sankey diagrams. It's not that convenient. I tried to use it a bit and I haven't gone very far, but maybe like it could be quite efficient to automate a lot of things, like if that's one big part of the issue. I'm trying to work on it and find a more user-friendly approach, but for the moment, that's the best thing I've found in terms of job optimization of the flow.
Cool, thanks. If you wouldn't mind dropping me that either directly or via Clemence in terms of what it's called. I didn't get that now, but
I put a link in the chat, and
cool. Great, thank you.
Okay, does anyone else have questions?
Just a remark as well. I know in Python that Altair, which is another visualization framework, is really good at automating those kinds of diagrams. So I have not compared it with Plotly, but I know it's very
how do you spell it?
Altair, Altair. Altair.
Okay, and does anyone online have questions? Well, in this case, I think we can stop now, as we had almost an hour and a half of seminar. Just as a reminder, we'll next in 2 weeks to welcome Professor Mario Giampietro, who comes from Barcelona. Well, it'll be online, but is in Barcelona, and we'll talk, well, so that that it catches Grégoire's questions about metabolism. For Professor Giampietro, we'll talk about the metabolic pattern of modern societies as a conceptual tool to study their sustainability. So that will, I guess, give further answer to that question.
Thank you, Harro.
Thank you again. Thank you very much for joining us, Professor von Blottnitz. And well,
So Harro, if you still have 5 minutes, I'm happy to talk with you.
Absolutely. Thanks very much, Gael. I'm still here.
Okay, so we just wait that, okay.